is already explained. Okay, so with alkyl aliphatic ethers you get, with excess you get this, with limited amount you get, okay, Br and OH, and with, if there is phenol aryl group, okay, so you get phenol and this. And this is another example, HBr. Okay, so let's solve a few more questions. Write this, write down the reagent phase. So preparation of ether, you can see we can use the method we've just shown. Yeah, Williamson synthesis. Okay, Williamson synthesis. Convert that to O minus and then react that with this. Okay. So yeah, Williamson synthesis, basically this is what Williamson synthesis is. Okay, convert that to phenoxide and then do SN2, right? That's how we make ethers. Right, what you are saying, I don't think that works. Okay, you are saying intermolecular dehydration. What? Yeah, that is also there, but this is more important method. That is also there. That is, what is the reagent? Do you remember what is used? So yeah, I know that's also there. You can use even that. So, but there you saying you convert that to OH. So yeah, this is more important method for preparation of ethers. Okay, Williamson ethers. This name, this is more important than that. But yeah, that also be done. Okay, next. Okay, and this will not work on the other type of bromide, you can say vinyl bromide. So suppose Br is directly here, then okay, because of the double bond character, this will not be so much reactive. And yeah, next. So first part is same, okay. Any H plus takes H minus plus O minus, and you get the ether, and then heating. Let me check this. Okay, so that you can ignore this part because that's required. That's really minimal, but up to A, right? That's again a Williamson ether. You can ignore this. Okay, this part is not required. Okay, and this also is, I think, yeah, is it related to this also? Can skip this one, you can skip this one, you can skip. Reduction also, this reaction I have given, actually this is preparation of benzene. You can use zinc, dust and acid. So OH is removed and you get benzene. Okay, fine, that's enough. Zinc, dust and acid you convert directly to benzene. Okay, next let's try this. How do we do this? Phenol to para amino phenol. Okay. No, but you cannot convert like that. No, Br to NH2 you're saying. Yeah, but your method will, how will you convert Br to NH? Right? Cannot use ammonia for doing that, right? Yeah, we need to get correct NO2 on para position, then reduce that, okay, to NH2. Now the thing is, we cannot do directly on directly on phenol. Generally it's not done nitration, because that makes that phenol also gets oxidized. Okay, the OH group also gets oxidized. So what is generally done is you make it convert to OCH3. Okay, or this is again like a protecting group. Okay, and then you add the nitrating agent. Okay, so separate the ortho and para and then reduce that to NH2 and again get back the OH group. Yes, so that's the basic method. You get para NO2 and reduce that. Okay, that This is the method to avoid oxidation of OH group. You can convert that to OCH3. Okay, that is again like Williamson synthesis, and then do the nitration and then separate. And zinc HCl will reduce, or other also you can use. LAH will also convert NO2 to NH2. What? How? But tell me again how to do that. That's an RX, okay. See, the problem with it's not a normal RX, this is with benzene ring. So Br lone pair is in resonance with the ring, so there is double bond character. So right, so NH3 will not do SN2 on that Br. That's what you say. I thought yeah. So otherwise you can do, but that's the issue. So we will also discuss separately, like aryl halides will not react all the time in a similar way to normal alkyl halides. Okay, this is next question. Synthesize metachlorophenol starting from benzene. Sulfonic acid and okay, nitrobenzene and fine. Then yeah. Nitro, we have to correct. Right. Nitrobenzene, then chlorination, then reduce, and then diazonate, right? So you can note this. This is how actually you can get meta groups, meta to some other groups, and convert that to OH later on. Right, so through NO2 and NH2 you can you can introduce groups at meta and then convert that to, actually you can convert this NH2 to any group you want, right, using this diazonium step, OH, Cl, F, Br, right. So I've given the whole list, right. So nitration, chlorination, and then reduction, and right. So this is a general strategy, and that is actually the main use of this diazonium reaction. You can convert, you can introduce any group you want. If you have NO2 through NH2, you can get any other groups. Phenol to cyclohexene. Okay. Let's skip this. At high pressure and high temperature, actually you can reduce this and then do dehydration. Okay. But this reaction is actually not that important. Okay. Next we have some special reactions for phenol. Okay. So this is called as the Kolbe's reaction or Kolbe-Schmidt reaction. So this is, I think, there in the NCERT book also. Okay. So this one you should know. We outline this first. Okay. So, or how to make salicylic acid and how to introduce COH group here. Okay. So first CO2 NaOH and then acid. So you have completed, Tushar, everything? Your portions are done? Okay. Right, so this is called salicylic acid plus OH, ortho to each other, and so you can say this is like reverse of decarboxylation. This is called carboxylation. Okay, so how this works, you have you know the mechanism. Do they have in NCERT mechanism over this? Okay. Can you try to think how this might work, looking at the intermediate and how CO2 will add on this carbon? But this is not EAS, or is it similar to EAS? It's somewhat similar, but it's not a typical. It's not so much EAS actually. Yeah, it will be converted to phenoxide, and basically from here this will react on to CO2. Okay, so actually not that difficult. It is right. Phenoxide ion reacts with COP, and then OH minus takes this H and convert both them to OH and OH. So it's somewhat like that, but not really. Right there, it's then you get a carbocation. Here you don't not getting any kind of carbocation actually here. But its first step is, yeah, it's like this is electrophile, this is nucleophile. So some way it is similar and some way it is not. So answer the next question. Synthesize aspirin via Colby's method, and you can start from phenol. Okay. This compound is called aspirin. OCOCS3SUH. Yeah, correct. So first first part is Colby's method. Make salicylic, and on that you add CH3COCl or anhydride. Fine. So maybe board exam also it can be asked like this, right? Synthesize aspirin. So aqueous NaOH, okay, and yeah, actually it's better to add here itself. It will be more reactive, phenoxide, compared to that phenol. This is more reactive. So we'll add and then add H plus, and you get another important reaction. I think this is also one in the text, right? And mechanism for this, no? Okay. Yeah, actually mechanism for this one is actually very complex. So let's see. Okay, so next reaction is this. You can note this. Dimer-diamine reaction. Okay, and this is used to make salicylaldehyde, which is common name for OH and CHO. This is the term formylation. Formylation is introduction of CHO group. Okay, so CHO group is called the formyl group, and adding formyl group to something that is called the formylation. Okay, so CHCl3NaOH, that is the so mechanism of this, actually it's actually slightly complex, okay, but we'll just go through this and it will help you to understand how this reaction works. Okay. So first step actually is which you should be knowing, like base OH minus and CHCl3, right? That gives carbene. So this reactor you should know. That is an electrophile, electron deficient. Okay, and also phenoxide will react just like the previous case. So till this point is very similar. Okay. So CCl2 is electrophile, carbene formed from. It gives CCl3 minus, and that gives CCl2. Okay, so that's how the carbon is adding on the ortho position, and then there is lot of things going on and finally converts to CH. Okay, but that is not really required so much. Okay, so this just to remember that that's how carbon adds. Okay, so that is the that's where the carbon adds. Fine, and then it converts to CHO. So you can see how this. So both chlorines are replaced. Okay, ultimately. this is the first here, and then OH minus reacts, and so both chlorines are replaced. Okay, and one with H, one with OH, and you get finally you get CHO, HO, and okay. Yeah, so and yeah, this mechanisms generally, same reaction can have different mechanisms also, slightly different. So generally the mechanisms which are most accepted, they are given in the textbooks. Okay, but like there can be different mechanisms of the same decision. Fine. So one point you can notice, if ortho position is suppose blocked by a group, okay, so major is ortho, but if suppose ortho is blocked by a group, then that case para at CHO at para position, or para formylation will occur, same reagent, right? So that could be one variation of this. Okay, but yeah, mainly you have to remember overall CHCl3 anyway, it produces CHO2, but ortho, if ortho is blocked, you get mainly a para. Okay. Okay, let's solve this, answer this. Okay, so A is your salicylaldehyde, correct? That is your Reimer Tiemann reaction. And next you go score. Here I have already given that is Cannizzaro reaction. So A is your C is just benzene. Yeah, I think this, let me just check. Yeah, intermolecular Cannizzaro you have to do, correct? So basically you're getting this should be better to write two products. You get two things here, so that will be, let's say this is B plus, okay, so that will make it more clear. This is B plus C, and let's say this is D. Okay, so because that is intermolecular Cannizzaro, so you get two things, right? One alcohol and one acid, and then yeah, right. So that is Cannizzaro I have shown here. Okay, OH minus reacts on C double bond O, and that gives H minus to this. Okay, and so this is what you get after the Canizaro and then adding H plus you get. Right, Kevin, understood? Okay. So in Riemann-Tiemann there is another same thing you can get if you react with CCl4. Okay, like it's similar reaction, but with CCl4 you get salicylic acid. Okay. So with CHCl3 we get CHO, and with CCl4 you get okay. So here carbene is not formed. Okay, this is different. It will be different. This is more simple. Okay, so you can see here how this works. Okay, so last step, all 3 chlorines replaced with OH and CO minus and then COH. So with CCl4 you get this. Okay. Okay, so this is again additional thing. It's other compounds can also give, like okay, pyrrole can give same type of. So other aromatic compounds can also give in a similar way. So it's fine. We'll solve this question. Yes, so how will this work? So using CHCl3, okay, first we get CHO, right, and convert CHO to COH and then do okay, acetylation on I think you can also you can use that will also be fine. Oxidize this COH and this, and using CCl4 it will give you directly this, right? CCl4 will give you, but that's actually the reason is cannot use very strong oxidizing agent because phenol gets the OH group itself gets oxidized, so that's the reason actually we're using a different oxidizing agent. Okay, so that is using CHCl3, and CCl4 will directly give you this, okay, and then you do acetylation on OH group. So okay, so that is it's about phenols.